supposed to get something with 50 seats more than this. And I do not know how the hub decides these things and why. I mean, they know that this class is one of the largest on campus. They really should be giving us one of the largest rooms. Can you hear me?
Yeah.
Okay. It's not yet time, I think. What is the time? 35. So first, have you given everybody a sheet?
Yeah, I think that.
Can you give me one? Just one. So I'll show you what to read. Here, let me do this for you. I like to know who you guys are. And I like to invoke you by name. So one of the rules in this class, if you fall asleep, I'll find you, I'll call you, and I'll ask you a question that you're probably unprepared for. So do not fall asleep, right? Fold this sheet in half, well, kind of half. And then fold each half in half inwards. And you got a nice little pyramid. Like so. Write your name on the front in big fat characters so everybody can read it and leave it here, right? Those of you who cannot, I'm sorry. Just if I look at you, just write your name on it and show it to me, right? I'm very sorry. Yeah. Also, this is the first time I'm teaching in person in 18 months. I have no idea how fast or how slow I can go. Things have changed. So I may run over, I may fall short. Most likely I'll run over because I'm probably, going to take more time to think about how I say things. It's very different. So just bear with me, and if I do run over, please don't abandon the class. I'll stop no later than 5 minutes late. Yes. May I know your name?
Connor. Do you mind just speaking up a little bit?
I'm screaming. This thing is useless, right? I mean, this is not. I'm supposed to get a microphone which actually projects into the speakers over here. They're supposed to have pickup speakers on top. Things don't work, right? So if you have problems, let me know. I'll yell louder, and that just means that in the next class I won't be able to speak, right? Okay, let's kind of start. Kind of, yeah. And I was supposed to also have a clicker. First things first. Let's see if this works. For some reason, okay, we're going to have to do it this way because for whatever reason this is not the down. All right. So welcome to 11785. This is probably going to be one of the busiest and toughest courses you have taken. Anything they told you about how hard it is, they were being nice. It's going to take more effort than whatever they told you. I'm warning you up front, right? So I'm hoping that by now you've already watched the logistics lecture. There's one up on the website and on MediaTek where we actually explain all the course objectives, logistics, how we deal with quizzes, homework policies, grading policies, and a whole lot of other stuff. If you haven't seen this lecture yet, please do so immediately. It's a bit long. I think Urvil recorded it. That's Urvil over there. Wave your hand. And how long is it? 28 minutes. It's going to be important, right? Part 2, you should already all have been signed up to Piazza. Also, you should have accounts on Canvas and Autolab. And if you've gone through the zeroth recitation, which has been up for about 10 days now, Then you all know how to set up your AWS accounts, and you all know how to get up on Google Colab. These are going to be the primary resources that we will have for computation. You've also received a note on forming study groups. Here's a secret that professors never tell you: you don't learn from us. We just stand here. We bring the brightest kids on the planet into one room, and you learn from yourselves. So to aid this, we recommend forming study groups. If you cannot form a study group of your own, we'll make it for you. We'll put you in one. And you must have all got yes. Yeah. May I know your name, please? Okay. I'm sorry. Can you also speak up? You are also wearing a mask. Pardon me? Yes. So every study group will be assigned a TA mentor. I'll get to that, right? Give me a second. So all of you, I'm yelling. When you talk to me, please yell too, right? So here's our course philosophy. We like to have, in my ideal world, every one of you will get an A, but you will have earned it. We don't inflate grades. That said, I think 7 out of 10 students in the last term got some version of an A. Every single one of them earned it. Nobody gets a free grade in this course. How do we make this happen? We have a philosophy: we don't like to leave any students behind. So we are going to do everything that we can to make sure that you get through well. We have lots of resources for you, teaching assistants. We have 20 of them almost. And they're the nicest people you ever met. That's how I pick my TAs. We are forming study groups. Every study group will have a TA mentor. We have something like 40 office hours every week. So make use of those. Then, of course, I'm here. Anytime you need, first in terms of questions, doubts, clarifications, provide feedback to your TA mentors or on Piazza or to me. If some things are not clear, sometimes I will actually do an extra lecture for you. Sometimes I'll hold office hours, whatever. But my point, again, is to make sure that you get everything. And then, of course, your classmates and friends, these are your biggest resources, use them. We have, the cheating policy is on the logistics lecture slides. We want you to solve all the quizzes by yourself. We want you to solve all the homeworks. The final submission must be your own. That said, we have nothing against you guys talking to one another and discussing things, because that's how you learn. So I don't care if you go off and discuss amongst yourselves, but then when you finally solve the quiz, you lock yourself in a room. When you finally do the homework, that code is yours. It doesn't mean that you can't ask your friend for debugging. So again, this is, you learn from yourselves, we encourage it. On the other hand, the final product must be yours. The line is fine. I think you guys are smart enough to know where it lies, right? Then, if you're, it's a heavy semester. This is not the only course you're taking, although we will pretend that it is. And so this means that you're going to be under stress. If you're under stress, if you find yourself getting poor scores, not being able to perform, not being able to keep up, don't just sit in a corner and get depressed. Reach out to your TA mentors. Reach out to me. We'll do the best we can to accommodate you. Besides, in spite of being one of the toughest courses on campus, we are also one of the most compassionate. We will try to help you. And again, in my ideal world, everybody's going to get an A, right? There is an attendance requirement. This is more important this semester than most, because many of you are internationals. I have to state to the university authorities that you have actually had a significant physical interaction in the class. Otherwise, you get designated as this gets designated as a remote course for you. It doesn't matter that you're in section A. You have to be here. You have to attend, right? So, and if that happens, then you're going to have visa problems. And that's on me and on the university. I cannot just say something about you and lie on your behalf, because if something happens, then the registrar is going to get pulled up. The president is going to get pulled up by the DHS. This can go all the way to the top. You don't want to be the cause of that. Attend, right? I have a way of making sure that you are in class, one way or the other. And every few slides, we will be posting a poll on Piazza. So in class, the only time you're allowed to open your smart devices is to track Piazza. And by the way, we will keep track of Piazza for questions from remote students, right? And when the poll comes up, please respond. We expect you to respond to every poll. That's how we track whether you're in class or not and whether you're paying attention or not. And I'm not going to score these polls. You will feel ashamed if you consistently score poorly, right? I assume you will. So any questions? Questions, anybody? All right, okay. The slides over here, I have to try this. This is annoying. I have a whole bunch of hidden slides that are supposed to be hidden, but this thing will not let me hide it. Why? Page down, page up, something work. My laptop's gone bad. Okay, too bad. So there are several slides here that were supposed to be hidden. I'm going to skip over those because I'm not able to hide them. They are on the slide deck on the course website. You're supposed to go through these. Every week there is a quiz, as you know. And the material that I don't present in class, but that's on the course website, will turn up in the quizzes. Right? And so, let's begin. Anything from you guys? No? Okay. So, why are you all here? Neural networks have basically taken over the world. They have become the paradigm for AI these days. You think of the AI problem, the best solution today is from neural networks. And this has happened very fast in the past 5 years. Suddenly, they've sort of blown up to achieve the state of the art and to exceed previous benchmarks by gigantic margins and get performances that were not only very difficult in the past, you're actually able to do lots of things that were simply impossible in the past. To give you some examples, speech recognition. We've been working on speech recognition since the 1950s. And yet, in 2015, if you used Siri, it was mostly for entertainment because you wanted to see what foolish thing it would do next. Then in 2016, something amazing happened. Microsoft published this article where they beat human performance on a fairly difficult task called the switchboard task, which consists of people talking to one another about random topics over a phone. And since then, the technology has only improved. These days, for a great many languages, your phone can recognize what you say better than you yourself can. Automatic speech recognition is that good. It's because of neural networks. Same thing with machine translation. In 2015, if you had translated something from English to Spanish using Google Translate, which was the best translation system at that time, and then if you translated the Spanish that came out back to English, what went in and what came out would be absurdly different. We used to use Google Translate as party jokes. And then around November 2016, something happened. Suddenly, these translations became real. They became good. And they became good enough that people whose job it was to translate now use Google Translate for the first cut before they actually go off and polish it. So it's actually becoming outperforming human beings, and the reason again is neural networks. Image segmentation, same thing. There is, you see the scene? I got this picture of Google, so I can't vouch for the veracity of this particular picture. But if you look at the scene, you see many, many, many objects in it, and every one of them has been sliced out and tagged. And it's been done very accurately. So for example, you have what? Human, the human's carrying a bag, there's a push cart at the back, there's a bicycle, there are buildings. Every one of them has been isolated and identified. This is all, this is something that maybe even we can't do, but a neural network can, right? Or there's some, I don't know if I can play this. This is from a company, I forget what it is. And this is real-time detection and identification of cars on a highway, done again using neural networks. And so on, many, many fields where we find this happening. Games. Now, ever since people began working on AI, it was assumed that the pinnacle of artificial intelligence was to be able to play mind games, like chess and like Go. And that's what people focused on. And then in 1992 or thereabouts, we built the first computer chess game that could beat a grandmaster. Anybody know where that was built? Right here. There was a PhD thesis for a student who wasn't even working on chess. He was actually working on hardware. Anyway, so we built Deep Thought back here in Wien Hall. And then those guys went off to IBM and they built Deep Blue, which beat Garry Kasparov. And since 95, no human champion, no human, has ever been able to beat the best computer chess games. But in chess, we thought was easy because it has only, 10 raised to 120 states. Go is much tougher. Go has 10 raised to 180 states. And so people generally assume that Go is never going to be beaten by, a computer is never going to be the best at Go. And then the Google guys came up with AlphaGo, which beat Lee Sedol, then the world champion. Now, 4 years later, you have computer games which can start from scratch without being told the rules. Figure out the rules and play and learn to beat AlphaGo in just a few moves. So that's how good they have become. They're amazingly good. Now, it's not just AlphaGo. You name the computer game and a great many other tasks. Computers can actually learn to perform the task and do an amazingly good job. And again, neural networks, right? Oh, here's this one. This is captioning of images. This is from 2016, 5 years ago. And you have all of these images. Look at the captions. Man in black shirt is playing a guitar. Construction worker, an orange safety vest is working on the road, and so on. All of these captions are automatically produced by a neural network. This was 5 years ago. And you can see they're really good, right? Girl in pink dress is jumping in the air. Now, it's actually become much, much better since then, in the past 5 years. When I say much better, like an order of magnitude better. And you would be fully, okay to imagine that these captions were actually produced by a human. They are that good, right? Other things neural networks can do. They've actually gone past being able to perform mere tasks, and they've actually gone into the realm of creativity. These are all pictures that have been hallucinated by a neural network. These people don't exist. So modern neural networks can paint faces, they can paint landscapes, they can generate music, they can write perfectly plausible stories. And all of these are fairly recent, the power of neural networks, and so on, right? The story continues. So many other problems, from art to astronomy to healthcare or even predicting stock markets. The things that you use are neural networks. So here are all of these amazing things neural networks can do, but what are they? Now, from where we stand today, at the beginning of this class, neural networks are these black boxes. They just take in some input and produce some output. Like they can take in a voice signal and produce its transcription. They can take in an image and produce its caption. Take in a game state and and predict the next game state. But what's in these boxes? What's the magic behind these boxes? Now, to understand that, perhaps we want to go back to something, to where it begins. Now, all of these things we saw, like recognizing speech, like captioning an image, like playing chess, these are fundamentally human actions. You don't see any other animals doing them. You definitely don't see rocks playing chess. So, and these are intelligent actions powered by a very specific organ, the human brain. So to understand how these things can be done, maybe we want to begin looking at the seat of human intelligence, the brain, to understand how we do it. Or even before that, maybe we want to consider the act of cognition. Now, human beings, our specialty is the ability to think. We can just sit in one spot and think. This is, I'd like to use this picture to represent this. This is Auguste Rodin's The Thinker. It's a statue of Dante, supposedly. But anyway, here are all the things humans can do. We can learn, we can solve problems, we can recognize patterns, we can create. And here's something specifically, especially amazing. You can just sit in one spot with absolutely no sensory or any other input, and you can produce thought, and you can generate outputs. You can cogitate, right? So these are the capabilities that we would likely want to emulate when we begin fashioning artificial intelligence. But then the question is, how do we do all of this? Now this question of how does human cognition work has been bothering human beings for a very, very long time. And the problem is, as Marvin Minsky said, if the human brain was simple enough to be understood, we would be too simple to understand it. So it's really it is an impossible task, but that doesn't stop us from trying. And so we've been trying for over 2,000 years. The earliest hypotheses about human cognition goes back to Greek times. So Aristotle, who came up with this, or was it Plato? Plato came up with the idea that it's all about associations. Does anybody recognize this painting here? Which one is that? The School of Athens, right? And somewhere in between, there's Plato and Aristotle in the middle. So this is Plato's hypothesis was that our thought process is based on forming associations. And this associationism was really the basic hypothesis for 2,000 years, till very recent times. So what is associationism? Now, here's something. Every time generally lightning is followed by thunder. Now, in your experience, anytime you encounter lightning, a little while later you hear thunder. Now, at some other point, if you hear some thunder, you're going to imagine, there probably was some lightning just a few seconds ago, right? Or if you observe lightning, you brace yourself to hear the sound. So you form the association, and you're making predictions and inferences. So the act of making these predictions is based on association. Now, this business of associationism is, so the idea that everything is based off association is actually a very strong and very good idea. It's actually at the foundation of all machine learning. But then when we begin thinking about the brain, the question is, okay, sure, we are performing all of these associations, but how does the brain store associations? It's all very nice to know what it does. Our problem is to figure out how it does it, because that's when you can model it. And so this leads to, and there were a great many strange ideas on how associations are stored in the brain, including an idea that all percepts in the brain are stored in the form of little vibrations in your skull which intersect, and some strange things. And we only began getting a decent hang of what happened when microscopy became really good. People studied the brain, and they found out that the brain is a giant mass of interconnected cells of a very specific kind, namely the neurons. And each neuron in turn has the structure that each neuron is connected outwards to many neurons, and each neuron has incoming connections from many neurons. So these connections are directed. It's just not a random mass of neurons. Every cell, the connections are directed. This was the discovery that we made in the 1800s. And then the first person to come up with a real model for how all of this works was Alex Bain. This was in 1873. And he formulated in this, Alex Bain, like all the scientists of those days, was a polymath. He was a philosopher, a psychologist, a mathematician, a logician, a linguist, and toughest of all, he was a professor. Back in the day, it was very hard to be a professor. Today, anybody can be a professor, right? Anyway, so in 1873, he hypothesized that the real information on how the brain stores its information was in the connections between the neurons. And he even came up with computational models for this. So he said that, he showed, for example, that by connecting the neurons up in a very specific way. Now the specialty here is that when you say the information is in the connections, you take the responsibility of doing very complicated things away from the basic unit, from the neuron itself. and you push all of that into the manner in which things are connected. And he showed that if you actually take some build networks of this kind, they can perform some fairly interesting operations, like this one here. Here in this example, this is one of Alex Bain's examples. All of the inputs are binary, they're Boolean. And any output here is going to fire if all of its inputs are on. And now you can see that if A and B are fire, then X fires. If A and C fire, Z fires. If B and C fire, Y fires. So there's one circuit, and for different combinations of inputs, you get different combinations of outputs. Now this is a single circuit. You don't change the circuit for the specific operation. Now this is something that we all take for granted, that you can have one function that produces different outputs for different inputs. In Bain's time, this was kind of considered heresy. People didn't quite get it. And he went on to postulate more, that the output can actually depend on the strength of the input. Here, for example, Y gets 3 copies of the input. X gets 2 copies. So if the input is low, then only Y will fire. If the input is high, both will fire. So again, the output pattern now depends on the strength of the input. He had other such ideas, and he also came up with a way in which the connections can be learned. So here's what he said. When 2 impressions concur or closely succeed one another, the nerve currents find some bridge or place of continuity, better or worse, according to the abundance of nerve matter available to the transition. Now, it sounds very complicated, but basically what it says is that if you have 2 neurons where there's some kind of an observable, something that looks like cause and effect, then those things will connect. And so this predicts a theory that came 75 years later from Donald Hebb. That's how much advanced he was. So this network here and the theory that he just came up with, they are basically modern neural networks. And so neural networks have been around since, artificial neural networks have been around since 1873. Now, the problem why it took until 2015 for things to really grow is this. This is a quote by Bertrand Russell. The fundamental cause of the trouble is that in the modern world, the stupid are cocksure, while the intelligent are full of doubt. And so in Bain's time, all of his colleagues thought he was talking nonsense, and they were pretty vocal about it. Eventually, he began to doubt himself. Initially, he did his computations, and he said that he figured out that if you want to have 200,000 percepts acquired, then you'd need about 1 million neurons and about 5 billion connections. These numbers are not off. They were actually pretty accurate. But then he realized that, a human being is not merely just 200,000 such associations. We have many more, and moreover, we have many partially formed associations. These things have to be built. And then he did the computation and figured that if you want to be able to store all of the things that we need to, then his model is broken, because it's going to require too many millions of neurons and too many billions of connections, and he thought the head was not large enough to hold all of that. So in 1903, he just sort of recanted. He said, "I'm sorry, I was wrong. Everything I said was rubbish. Please forgive me," and he died. And unfortunately for him, and fortunately for us, he was right in 1873, and he was wrong in 1903. The human head is vastly complex. We have over 80 billion neurons in our head. We have over 100 trillion connections. There's more than enough capacity for everything Bain thought of and a whole lot more. And so today, we realize that the human brain is fundamentally a connectionist machine, as described by Bain and Ferrier back in the 1800s. Neurons connect to other neurons, and the processing capacity of the brain, the ability to form associations between percept and percept, between input, stimulus, and response, that is held in the connections between the neurons. And so your modern neural networks, they are connectionist machines. They emulate this structure. Now, what's the difference between, so here's what a connectionist machine is. It's a network of processing elements. And all knowledge about what the machine must do, how it must operate, is stored in the connections between the elements, which are themselves very simple and very stupid. So now, neural networks are connectionist machines as opposed to modern machines. The architecture that you have on your standard laptop, on your phone, anybody know what that architecture is for the processor? Pardon me? It's the Harvard architecture or the von Neumann architecture. And how many of you have heard of this term, the von Neumann architecture? Raise your hands, right? Some of you, many of you haven't. So when I have something like this, a phone like this, how does this work? Is the processor the program in your phone? So then what happens here? How does the phone work? How can the same processor do many different things? So this is the architecture that von Neumann came up with in the 50s. The idea is to have a central processor and a separate memory structure which holds programs and data. And anytime you wanted the processor, so now the processor itself is a fairly complex object which can do different things. It can add, it can multiply, it can perform different actions. And now anytime you wanted the processor to do something, you would fetch the program and the data from memory and it would do it. Now, the flexibility here is that this means that the same machine can be made to perform thousands of different operations simply by changing whatever is in memory. You change the program. What about a connectionist machine? In a connectionist machine, the architecture is the program because the program is in the, what's it in? The connections. The program is in the connections. That structure in its totality is the program, is the memory, is everything. So if you want to change the program, you have to change the machine. Which is why when you implement neural networks, nobody goes out and builds hardware neural networks these days. You emulate it on a Harvard architecture machine. Anyway, so a quick recap of everything we've seen so far. Neural network-based AI has taken over most AI tasks. These originally began as computational models of the brain, or more generally as models of cognition. The earliest model of cognition was associationism, and the more recent model is connectionist, where neurons connect to neurons, and the workings of the brain are encoded in these connections. And so current neural network models are connectionist machines. At this point, we have a poll on Piazza. Please get on Piazza. There are two polls. Post number 55 and post number 56. Please respond. And take any questions, yeah. Go ahead and take it anyways. Pardon me? So you go to Piazza, post number 55 and 56. Here are the polls. 55, 56, this is 1, 57, 58, and 59. So we have 4 polls. The first one has 2 parts. But right now we're just doing poll 1. We'll time it, right? And just let them know. 20 seconds, guys. I have to rush because I have to finish my class. Yes. You go to Piazza, the Piazza post. You go on Piazza, and the Piazza post number 55 and 56. I'm not really going to count today's polls, but today is where you get used to how this thing works, right? Okay, how many did we get right? No, but how many were correct?
161.
And the second?
Second one
Okay, guys. Most of you got, anyway, I'm going to continue. Most of you got these questions right. I assume you're paying attention. Thank you. Right. So here's where we are. Connectionist machines are networks of processing elements. Now, the first connectionist model was actually proposed by somebody we're all very familiar with, Alan Turing. And there's some information. Alan Turing invented everything anybody ever thought of. So there's information about this on the slides. Take a look. And this will appear in the quiz. So now all world knowledge is stored in the connections between the elements. The elements themselves, we claimed, are going to be very simple. So what are these elements? To understand that, we are going to go right back and look at the brain. The basic units of the brain are the neurons. Now, this is what a neuron looks like. It's got this big head. Where's my pointer? So it's got this. It's perfect, right? So it's got a giant head, and which has all of these connections, incoming connections called dendrites. That's where other neurons connect to this neuron from. And the strength of the connection of one neuron to the other depends on two factors: the size of these dendrites and how many dendrites it connects to. Now, depending on the total response from here, the head over here generates spike trains, which travel down this long leg and go out to other neurons from the end. Now, this long leg called the axon, it's protected by fat. It's called the myelin sheath. And when people studied Einstein's brain, they found that the difference between his brain and normal people's was not in the number of neurons or connections. It was in the amount of fat in his head, which protects the neurons. So it turns out how smart you are depends on how much fat you have in your head. So being a fathead is a compliment, because that's and that's literally true, right? And now here's another factoid that only interests me, maybe. Neurons never undergo cell division. They cannot, because if a neuron underwent cell division, all the information in the neuron is lost. So neurons can be generated from neuronal stem cells, but they never undergo division, which is why you're born with all the brain you're going to have. After that, you may gain itty-bitty, new cells from neurogenesis, but you can rest assured that the brainiest you were was the day you were born. Anyway, here's what the neuron looks like. Now, at a rough level, you can think of this as the neuron getting a lot of inputs from the other neurons that it's connected to. And when the total signal from all incoming neurons exceeds some threshold, it fires. That firing signal goes out the axon to other neurons. And so we need a computational model of the structure. And the first guys who came up with the computational model were these two. One of them is a professor, the other was a hobo. Anybody want to take a guess who is who? So who's the professor, do you think? The left or the right? Raise your hands if you think the guy on the left is a professor. And how many of you think the guy on the right was a professor? Okay, you're right. So that's the guy to the right is Warren McCullough. He's there sitting, drinking some wine. And the guy to the left is Walter Pitts, who was 19 years old. And he had never been to college, never been to school. Just used to correspond with Bertrand Russell. And ended up at Warren McCullough's door. And Warren McCullough took him in, and they worked on this problem of modeling the neurons. And in 1943, when Pitts was only 20 years old, they came up with this immensely complex-looking paper which says a logical calculus of the ideas immanent in nervous activity. And this proposes a model for the neuron. It uses a lot of very complex symbolic math, which people still have trouble following. But here's the gist of it. Here's the model they had. This triangular head over here, that is the neuron. And the colored lines represent incoming connections. Now, the green lines represent what are called excitatory connections. They make the neuron fire. The red line is an inhibitory connection. If there's any signal coming up the red line, the neuron will not fire, regardless of what excitation it gets. And if the excitation exceeds a threshold, and if the inhibition is off, the neuron will fire. It's a very simple model. And they showed you can do all kinds of things with it. So in all of these examples, the neuron fires if there's a total of 2 inputs coming in. And every line takes a single unit of time for the signal to travel. So this guy is just a delay. 1 fires. A little while later, 2 gets 2 copies of 1. 2 is the threshold, so 2 will fire. This one over here. Can anyone guess what this is? Victoria. What would that be? The one to the top right. Anyone else, Rucha, here?
I think it's an OR.
It's an OR. You're absolutely right. If either 1 or 2 fires, then the neuron gets 2 inputs, and so it's going to fire, right? And Yiming, what is this one here to the left? Here. That's an AND, right? And what about the 4th one? That's a more complicated function. It's 1 and not 2. Because if 2 fires, it's not going to fire, right? So it showed you can actually build some fairly complex structures. And this is a particularly interesting example. This is modeling heat and cold perception. You have 2 sensors, the cold receptor and the heat receptor, and the cold sensation and the heat sensation. Now, you'll observe in real life that if you touch something very cold, very briefly, your initial sensation is not of cold, but of heat. You have to touch it for a prolonged period of time for you to actually sense cold and not heat. And they showed how you can model that with the structure. So here, if the cold receptor, here the blue neuron is just a delay. It takes a signal, and then 1 unit of time later, it forwards it on, right? The red neuron is a little more complex. It gets a connection from the blue neuron, but it also gets an inhibitory connection from 2. Now imagine what happens if you get a very short cold signal. Then that cold signal goes up here, and it also goes here, but because this is a delay, there's nothing coming out of here. So this guy gets only 1 signal, it doesn't fire. A very short cold signal produces no sensation of cold. But if it's prolonged, then at time instant 2, this guy is still giving you cold, this guy is giving you the delayed cold. Together they will give you a cold sensation. Now what happens with a very short cold sensation? With a very short cold sensation, after 1 time step, it goes here. After 2 time steps, it goes here. But this guy is off. So this is going to fire this one, and you will actually sense heat. But if you have a long cold sensation, then after 2 time steps, this guy is going to get a signal out here. But because this is still on, it inhibits the red node, and you don't sense heat. So, they showed that you can do all kinds of really fancy things with this model. The problem was they had no hypothesis, no algorithm for how the network could learn to perform things. Also, their claims were a bit too tall. They claim that it's Turing complete and it can do all sorts of things. And so overall, although it was a very nice idea and the start of modern neural networks, the idea itself didn't go very far. The first learning algorithm came from this guy, Donald Hebb, in this paper called The Organization of Behavior in 1949. Now, Donald Hebb was a very interesting guy. He started off trying to be a novelist. Then he decided to become a school teacher. Then he became a farmer. Then he became a hobo. Then he said, okay, screw it. I'm just going to become a psychologist. So he became a psychologist with a PhD from Harvard. And so he came up with this idea for how neurons can learn, how the brain might learn. And this is a very complex sentence over here which explains it, which says, when an axon of a cell A is near enough to excite a cell B and repeatedly or persistently takes part in firing it, some growth process or metabolic change takes place in one or both cells such that A's efficiency as one of the cells firing B is increased. It sounds complex, but it's much more nicely and succinctly stated as neurons that fire together, wire together. So what this means is that if I have 2 neurons with some connection between them, and if both neurons fire at the same time, then the connection between them gets stronger. That's the basic hypothesis over here. And so you can write this, and here's how you explain it. Now, when you have a synaptic connection between one neuron and the other, the synaptic connection comes through this thing called the synaptic head. There's really no physical connection between the two neurons. You have a synaptic head, this big blob, and then the synapse to which it is adjacent, and you have chemicals going out of the one triggering the other. And anytime both of these fire at the same time, then this head gets larger, and so the connection becomes stronger. So he even gave a math model for it, which is given by this here. If WXY is the connection between two neurons, then after each stimulus response, that changes to WXY equals WXY plus some eta times XY. So observe that if both X and Y become 1, if both fire, the weight increases, otherwise it doesn't change. Now there's a problem with this. So Richard, what's the problem with this? Pardon me? You don't see anybody? Does anyone see a problem with this? Pardon me? Yeah. What were you saying? It's just good. There is no decrease, right? It keeps on increasing. It's unstable. If you wait long enough, every connection is going to be saturated, and it's going to be an uninformative network, right? So it's fundamentally unstable. Stronger connections will enforce themselves. There's no notion of competition. There's no reduction in the weights. And so learning is unbounded till it's not learning at all. Eventually, it's just going to get saturated out. People proposed all kinds of fixes like this generalized Hebbian rule by Sanger, various others. They're really not of interest to us. The basic point is, while the Hebbian learning rule is actually a very nice idea, there's something broken about it in that there's no unlearning, there's no fading of weights. And so we have our second poll. That one is 57. The students in?
Stream are not able to see where you're
Oh, okay. All right. Ask them if they can see the mouse. Actually, there is no mouse. For some reason. Where's Chauran? Just stop it when it's done, yeah?
10 seconds to go.
So, can you do me a favor? Go to my office. There's a USB mouse there. Can you bring it?
Okay, sure.
All right. Okay, guys, I'm continuing. How many got it right? Purve? How many got it right?
Yeah.
94%. Not bad. Okay, you guys are improving. Now, questions, anybody? Any questions? Okay. So now we are beginning to get into modern times. The model that we currently use was proposed by this guy, Frank Rosenblatt. He was like people in those days, he was everything. So he was a psychologist and a logician, and he invented the solution to everything, also known as the perceptron. His model was very nice. His original model, of course, the way he proposed it, it was a very complex model with afferent and efferent connections. It was trying to model the eye. But for our purpose, we will simplify it. Here is the model. Let's say the model for the neuron was like so. There's a single unit which takes in a number of inputs and receives a weighted sum of all of the inputs. If this weighted sum exceeds a threshold, then this neuron fires, otherwise it does not fire. Right? So that's the threshold logic. Just a second. Excuse me? So can you do me a favor when I go to the screen and point? Because, yeah, the students are not able to see it. Yeah. So this is the basic simplified model of the perceptron. And now this model is, turns out it's actually very powerful. We'll see this more of this in the next class. And it was originally assumed that this model could, this model could compute any Boolean function with appropriate setting of weights. And people got so hyped up that even the newspapers came on board. The embryo of an electronic computer that the Navy expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. This was the New York Times in 1958. Frankenstein monster designed by Navy that thinks, Oklahoma Times, 1958. You can imagine that this is a great deal of hype. And Rosenblatt believed it himself. This was the cause for, he even came up with a very nice learning algorithm for it. So if you were trying to perform a Boolean task, for instance, he showed that this learning algorithm works just fine. That, say you have some input x, and the connection, the weight of the input is w, then in response to this x, the actual output of the perceptron is some y. The desired output, what you want it to be, some d. If d and y are the same, that means the perceptron is doing its job. There's no need to modify the weight. If d and y are different, then you want to change the weight in the direction that is going to push it towards being correct. So you change it in proportion to the error between the desired and the actual outputs. It's a very nice learning algorithm. And more importantly, he even showed that if you've got two linearly separable classes, this is eventually going to give you the correct answer. Yes?
Yeah, I asked, like, why when we are taking the weight, why are we multiplying the input as well? Like, if the input is super large, it won't be the weight be like influenced too much.
We'll get to that when we talk about training. But for now, we can just agree that this is going to be. In fact, we'll talk about it multiple times. But think about this: the output is Boolean, right? And so d minus y is going to be either 0, or plus 1, or minus 1. That's it. So you're adding or subtracting the input. That's it. Some small fraction of it. And sure enough, this perceptron model can compute all kinds of things. Again, in this figure, the number inside the circle is the threshold. If the weights above the lines are the numbers above the lines are weights, and if the weighted input matches the threshold, it's going to fire. Otherwise, it won't. So given this, can you see it from there? So what do you think the top left figure is?
Trying to predict
Yeah, but if it's a Boolean operation, what is it? It's an AND. Perfect, right? So this person in the far corner over there, I can't see your name tag. Yeah. Okay, James. What is the second one? The top right. Pardon me? Anybody else want to tell me what that is? That's a NOT. When the input is 0, it matches the threshold. When the input is 1, the weighted input is minus 1, so it's not going to fire, right? The one at the bottom clearly is an AND. So as you can see that these things can actually model all simple Boolean gates. This is what fooled Rosenblatt into thinking it could model any gate at all. The problem is that it can't. And that's what Minsky and Papert discovered in 1968, that there is no setting of the weights that can make an XOR. Those of you who are electrical engineers recognize this as a threshold gate, and you know a threshold gate cannot compute an XOR. So, and as soon as this was discovered, then people became very dismayed, and all funding into AI research disappeared for 10 years, which is why we are behind. But then the solution lies in looking at the brain again. Now in a brain, the brain is not just one giant neuron. It's a connection of neurons, right? So the brain is actually a network of neurons, and this is what Minsky and Papert pointed out. If you begin networking things work. So here is how you would compute an XOR. You don't do it with a single perceptron. You do it with 3 perceptrons connected in 2 layers. The first layer has 2 perceptrons. The first one computes X or Y. The second one connects not X or not Y. And then the final one ANDs the 2, and now you get an XOR. So this just a little bit of terminology over here. You don't really need to see the outputs of the neurons in the first layer. So while it doesn't mean that you don't want, you cannot see them, it's not required. What is essential is the number that comes out of the final neuron. So we will call the guys in these intermediate layers whose actual immediate outputs are not directly relevant, we'll call them the hidden layer. The entire structure is a multi-layer perceptron. It's layers of perceptrons. And so once we begin looking at multi-layer perceptrons, we realize you can compute all kinds of Boolean functions, like this really horrible, ugly Boolean function I have over here of 4 variables. This can be computed by a very simple MLP, the one that I have there, right? And so what this means in cognitive terms is that a multi-layer perceptron, a network of perceptrons, is a universal Boolean machine. What I mean by this is not that the MLP can compute, a single MLP can compute any function. What I mean is that if you give me a Boolean function, it doesn't matter how complex, I can construct an MLP which computes it. So a multi-layer perceptron is a universal Boolean machine. And so our story so far, neural networks began as computational models of the brain. These are connectionist machines. And the McElroy-Pitts models neurons as Boolean threshold units. They provided no learning rule. Hebb came up with a learning rule, but it was unstable. Rosenblatt's perceptron is a variant of the McElroy-Pitts neuron with a provably convergent learning rule. But individual perceptrons are limited in their capacity. But networks of perceptrons can model arbitrarily complex Boolean functions. Questions? Nothing? Okay. Any questions on Piazza? None? Okay. So here's the important thing. Our brain is not Boolean. The world is not a Boolean place. The inputs are real valued. And we make non-Boolean inferences, right? So how can we extend this model to this world of reals? Very simple. Here's how the perceptron operates with reals. Let's consider a perceptron which makes Boolean predictions based on real inputs. In that case, the perceptron is going to have, again, a collection of inputs, but they're all real numbers. The weights are real numbers. And the perceptron is still going to look at the weighted sum of inputs. It's going to fire if the weighted sum of inputs exceeds a threshold. Now, there's a slightly different way of looking at it. You can, instead of having a weighted sum being compared to a threshold, instead I can say I'm just going to look at a weighted sum plus a constant. And and the neuron fires whenever this weighted sum plus a constant, plus the constant is positive. Otherwise, it doesn't fire. Now, and if I said B to be the negative of the threshold I saw earlier, then this is exactly the same model, right? So this is just restating it. Now, there is a word for this kind of combination of variables. Anybody know what that is? Did you say that? Someone said it. You. Affine, right? So that's an affine combination. What's the difference between just having just the sum versus having the sum for the bias, the sum plus the bias? If I just looked at a weighted sum of inputs, what would you call it? That's just linear. And what's the difference between linear and affine? So linear is summation WIXI. I mean, there's a lot more, there will be other ways of defining it, but it's something like this, right? Affine is summation WIXI plus B. And the real distinction shows up when you try to equate the 2 to 0. When I try to equate the 2 to 0, the linear is always going to go through the origin. If all the x's are 0, then the sum is 0, right? Affine is not going to go through the origin. It's going to be, and affine is a generalization of linear. And so we can say that the perceptron is computed by applying a threshold function which outputs a 1 if the input is non-negative and 0 otherwise, on an affine function of the inputs. So once I see this, I can actually sort of generalize this. I can change the threshold function for something else, like a sigmoid, which is a smoother version of a threshold. And you can think of the output as the probability of firing. Or I can change this to something else, even any arbitrary function, any real valued function. And so now we can think of the perceptron as computing an affine function of its inputs and then applying an activation to this affine function. Now, that's the perceptron that you guys are going to be working with. But for today and to the next class, we'll consider assuming the threshold activation because it provides really good intuition. Now, continuing with the threshold activation, here is what the perceptron is. It outputs a 1 if the weighted sum exceeds a threshold, 0 otherwise. So in some region of the input space, the output is 1. In the other region, the output is 0. And the boundary between the two, that's when this weighted sum exactly equals the threshold. What is that an equation for? Anyone? You in the corner? Yes. Yeah. What's your name again? Eric. Okay, so what's that an equation for when this weighted sum is exactly equal to the threshold? Yuan? No, so but what is that? What is this? That's a hyperplane, correct? That's why, so this is the linear classifier. There is a hyperplane of this kind. And whenever the input is on one side of the hyperplane, the output is going to be a 1. When it's on the other side, the output is going to be a 0. If the input is two-dimensional, then I can draw the whole function in 3D. And then that function is going to look like the step function. It's what's called a Heaviside function. And it's 0 till it arrives at a line and then becomes a 1. And so once you realize this is what a perceptron does, you can figure out why it works as Boolean gates. Now, if your input is Boolean, and if you have two inputs, the inputs take the value either 0 or 1. So the inputs are going to be in one of those four corners, right? If I build a perceptron with this boundary, what Boolean function does this compute? That's an OR. The one to the right? That's an AND. The one to the third one? That's ignoring x1. It's a NOT on x2, right? So you can see, and now from this you can see why you cannot compute an XOR. And if you haven't figured this out, we'll see this in the next class. But then once I can compute that, I can do other interesting things. I can compute this complicated decision boundary such that I can construct a multilayer perceptron which outputs a 1 when the input is inside this pentagon and a 0 outside. If I asked you to do it, Zishin, how would you do it? Anybody else want to take a guess? You guys at the back? That young lady there is hiding her eyes because she doesn't want to be pointed out. You guys? Yes. Yes, Maxwell. How would you do it? Beautiful, right? He nailed it. That's exactly how you do it. I'd have one perceptron for this guy, a 0 below, which produces 0 below that line, and one above. A second for this one, a third for this one, a fourth for this one, a fifth for this one. Now observe that only for input inside the pentagon are all 5 perceptrons producing a 1. Everywhere else, at least one of them is producing a 0. So now I just need an AND as a final perceptron which checks if all 5 of them are producing a 1, voila. I've got a pentagonal decision boundary, right? Once I do this, I can do something more complex. I can have this decision boundary, a double pentagon. I'm going to have one subnetwork producing the first pentagon, a second one producing the second pentagon. I OR the two, and I get a double pentagon. Or I can do something even more complex. I can produce these crazy boundaries, right? So again, Maxwell, how would I produce that horse-shaped boundary? There you go. He answered me, right? You can chop it up into you can chop it up into many little pieces, and then you can compose it as a composition of many polygons, right? So, and so now when you think of some task like classification, you get an input image. It's a 784 pixel image, if like in the MNIST corpus, which you will encounter. You need to say whether this is an image of a 2 or not. Now, if you think about it, these inputs live in some 784 dimensional space. There's some region of the space that actually represents the digit 2. Everything else represents not 2. And so all I need to do is to compose the function that produces this outputs of 1 inside the space and 0 outside. In my figure, the peanut represents this region that encloses a 2. Yes?
We use lines. Does it mean like if we have a circular boundary, we will never perfectly...
Thank you. We will address that in the next class. That's a brilliant question. Next class. Be here, right? So here's the story so far. MLPs are connectionist computational models. Individual perceptrons are computational equivalents of neurons. It's a layered composition. An MLP is a layered composition of many perceptrons. MLPs can model Boolean functions. They're universal Boolean functions, meaning you give me any odd Boolean function, I can compose an MLP for it. Individual perceptrons can act as Boolean gates. And networks of perceptrons are Boolean functions. Now, MLPs are also what I'm calling Boolean machines, in that I can represent Boolean functions over linear boundaries, like we saw in the case of the Pentagon. They can, in general, they can produce categorical outputs if I have multiple outputs. So MLPs can represent decision boundaries. So this means they can be used to classify data. But then there's a pole. This is pole 58. I got to figure out how to deal with these guys. I never get to see them. Yes?
Can a perceptron with real numbers be trained for a complex function?
Yeah. Next class and next classes. That's what this entire class course is about.
No, I'm not able to find it.
Pardon me?
We're not able to find the pole.
What, pole number 58? Oh, so Woodville, open 58. He says it's open. Okay, we are still sort of ironing out the kinks. If you haven't found it, wait. Is it up?
Yes.
Okay. Huh? Okay. 59. Okay, 59 could be खोल देना वैसे, ठीक है? Open 59 as well, just so we don't. Yeah. Wait, did you get the mouse? Yeah. Where? Uh-huh. Shoot. Did I just kill this? Someone help. Okay, do it. I'll have to debug my machine. Okay. Questions, anybody? Any questions? Yes.
So in the previous slide, we already know how many edges or lines we want.
Correct.
But what if we don't know how many lines we want?
That's what you're going to spend the rest of the semester figuring out, right?
Okay.
So all we are speaking of at this point is that what it can do. And what we are finding is that it's very flexible, which is why we're able to perform all of those magic operations, right? Now we've got to go on to say, how do we make it do something specific that we want it to do? So in fact, we haven't answered even this question. What about continuous valued outputs? We've talked about Boolean outputs. We've talked about, Boolean outputs in response to Boolean inputs. We've talked about Boolean outputs in response, or even categorical outputs in response to real valued inputs. But what if you want to model an arbitrary function, a continuous valued function? So for example, let's say you want to model a function like this, this cape, right? Can we build a network which actually models that? And the answer is yes. So to explain, we'll look at a function of a scalar input. So here there's just a single input x. And now consider this very simple circuit. It has two perceptrons. The first perceptron fires if the input is greater than T1. The second one fires if the input is greater than T2. And let's assume, without loss of generality, that T1 is less than T2. Now, their outputs are summed up. The output of T1 is combined with a weight of 1. The output of T2, the output of the second neuron, is added in with a weight of -1. How does this neuron respond? Anyone? You guys at the back, one of you? What's your name? Show me a bit. I can't read it. I need a telescope. You need to write bigger than that. Okay. All right. Anyway, so how would this respond?
It's just a square.
It's just a square. It's going to be an output. Write it bigger. And okay, all of you, bring your tags next class. I need your tags in every class. Okay. So save it. If you increase the input from -infinity to +infinity, when the input, so long as the input is below T1, the output is 0. Then it becomes 1. Then after it goes up beyond T2, it goes back to 0, right? Now tell me this. Given just this guy, if I want to model a function of, say, this shape, how would I do this? Anyone want to take a guess? Johan, how would you do it? I know Maxwell has an answer. Okay, yo, guess.
You make like a bunch of squares.
Perfect. There you go, right? These guys answer all my questions. So here's what you do. You chop up the range into many little pieces, and then you're going to have one little pulse for every segment. That pulse is going to be produced by one subnet with 2 neurons. And then I scale their outputs and add them up. Now, is this going to be an accurate representation? What is it? It's an approximation. How precise is the approximation? It's arbitrarily precise. I can make it as precise as you want to. So I can approximate pretty much any continuous valued function as well. This is just for scalar inputs, but clearly you can also do this for vector inputs, right? So what this means is a neural network is not just a universal Boolean function. It's not just a universal classifier. It's a universal approximator. You give me a function, I can compose a neural network that approximates it. So there's one last point. ठीक है बाद में ना पियाजा पे आंसर्स पोस्ट कर देना Okay, guys. We are at the end of the class, and I can't believe it. I almost timed it to perfection. 9:55, they said. Okay. So here is the story so far. Just to summarize everything we've learned in the class so far. MLPs are connectionist computational models. They are classification engines. They can identify classes in the data as we just saw. Individual perceptrons are, well, there's some bullets that I'm missing information for, let that be. They can also model continuous valued functions, right? So here are other things that we saw that there are universal Boolean functions, universal classifiers, universal approximators. Here's something else they can do. All of the MLPs that we've been looking at so far are going, hey there, do you mind turning the phone off? So, what's your name? Saida, okay. I'm not asking you to keep track of who had the phone on, I just need to know your name, right? That's okay, all right. So, if you fall asleep in my class, I'll send you out with some money to buy yourself coffee. Don't do it. It's very embarrassing, right? Anyway, here are other things you can do. You can model memory. Everything, all the networks that we saw so far, you had information flowing left to right in one direction. What happens if things go back? It turns out it can model memory. There's a very nice, it was originally proposed by Lawrence Kuby in 1930. It's the basis of Boltzmann machines and Hopfield networks. You're going to learn later in the course that they can represent probability distributions over integer domains, over real valued domains, even over complex valued domains. They can model the a priori distribution of data and the conditional or the a posteriori distribution of data. They can do this. So it's not merely about computing functions. They can also be models of probability distributions. They can generate data from very complicated and uncharacterizable distributions, like generating faces. What does the distribution of faces look like? Nobody has a clue. You can't find a domain where you can put a function to it. But nevertheless, a neural network can produce a sample from this distribution. It can produce a sample from the distribution of landscapes. They are very powerful things, right? And so we have this common joke that the hardest thing in the world to do is to rub your stomach and pat your head at the same time. It turns out there are actually competitions for this. And of course, it's got to be an Indian who wins it. So, but anyway. And that guy he's out on YouTube. It's embarrassing. Anyway. So, in AI, what is a neural network? It's just a function. It takes an input, it computes the function layer-wise to predict an output. And more generally, given one or more inputs, it predicts one or more outputs. And so here's where we began, right? What is inside all of these boxes? What are these magical boxes that do all of these magical tasks? If you think about it, each one of these operations is a function. It takes an input, it produces an output. That's all it is. And what we learned is that a neural network can approximate pretty much any function that you can think of. So these guys are all just neural networks. That's why a neural network can perform all of these actions. So what is the real magic over here? The magic is in figuring out A, how do you represent the input? How do you represent the output? And then how do you learn or how do you construct a neural network that computes the appropriate function? That's about it. When stated in those terms, the whole thing looks very simple, right? And so that's all it really is. It's actually very simple. And so here's where we'll end today. The final statement of the day, interesting AI tasks are functions that can be modeled by the network so long as we figure out how to compose them in terms of how to represent the input, how to represent the output, and how to build the function, the network in the middle that computes the requisite function. So, and we'll stop there. Next class, we are going to spend a lot more time. We've spoken of what a network can do, but the network has structure. So we're going to learn about, what are the restrictions on the structure, what are the requirements on the structure, what we are here speaking of, deep networks, deep learning. What do we mean by deep? And what is the necessity for depth? These will be part of the next class. If you have any questions, post on Piazza. There is a Piazza thread for the lecture, so that's where you will post it. See you all on Wednesday. Thank you. Yeah, just leave it there.
Sir,
Yeah.
since I'm an international student, I would have to take at least 2